Thank you so much for the introduction, and it's a pleasure to be able to speak here today. And this talk is going to be, I think, something completely different, so hopefully you'll enjoy it. I have some very interesting case studies in what we deal with kind of on a daily basis in the CDMO space. And really, Crystal Pharmatech has gotten into the formulation CDMO space several years ago. And why we did it was really, we felt that there needed to be a revolutionary change in the way that formulation development takes place in the CDMO. Not having a siloed approach of early formulation into formulation development. And so we merge all of the early formulation with the late stage formulation development to really understand the molecule and move the molecule forward. Just a brief introduction of who we are. We have locations in Cranberry, about 20 minutes up or down the road. We also have GMP facilities in Canada for phase 1 solid oral dosage and GMP facilities over in China. So when I talk about this revolutionary change to formulation development, it's nothing new, right? It's just understanding your molecule, understanding the material, and making the medicine. We kind of stole this from a conference that started in around 2011 by Elizabeth Vadas and Ern Almerson. But very early on, understanding basically your business strategy, what your clinical strategy is, and understanding your molecule very early on in development. So all the way back in late lead optimization or early candidate selection, and understanding accurate solubilities for the compound, understanding potential crystal forms that can exist, and benchmarking your compound against industry standards. So there's a ton of literature out there on how BMS, Merck, Pfizer, how you guys develop your compounds from a developability assessment. So we scanned through the literature and took all those best approaches and came up with our own developability assessment, which we start again in that candidate selection, late lead optimization. But it's getting that fundamental understanding of your molecule. That leads right then into the step 2, which is the form selection process. And what I want to point out here is we often see with a lot of CDMOs in this space, you'll see a salt selection, then you'll see a polymorph selection, then you'll see a spray dry dispersion. So we want to condense this and really do this form selection as a one and done. Right? So when we do a form selection, we want to do fundamental understanding of the thermodynamics. Do you really need a salt, or do you really need an enabled formulation? What's that PK study finalization that's going to drive that decision on your form? And then going to your medicine, how do all these variables fit into your target product profile, and really tailoring the formulation. So we minimize the number of prototype formulations because we understand the molecule, and that allows us to use less material and speed you up to phase 1. But I have some pretty interesting examples here of compounds where that early understanding of the molecule really impacted the development and impacted the client. And with this understanding, kind of how their development could have been sped up. And so compound 1 is a non-crystalline API, BCS3. The client had limited API available and was hygroscopic. It showed gelling. We saw bearding with enteric coating, and there was gut degradation. So a really good compound. And to go over some of the issues, this was a prodrug that converts to the parent. The prodrug itself was BCS3. The parent drug was BCS2. The API was susceptible to hydrolysis degradation in acid solution. And when we enteric coated that, not when we, but when they were enteric coating with their previous CDMO, was leading to bearding. The API was amorphous, and you can see the, hygroscopicity profile, and we actually saw gelling at the high relative humidity. and that led to a lack of disintegration and incomplete dissolution in tablets. And again, very limited amount of API, 130 grams with the high dose levels, and it's not compatible with basic excipients. And so in understanding the molecule, we were then able to change the stability conditions. So the API was stored at 5C, drug product at 2560, did all the manufacturing at low relative humidity, pack in a foil blister, and actually monitoring the hydrolysis during dissolution. So how did we resolve the gelling, disintegration, and dissolution? The API was micronized and then coated with a hydrophilic colloidal silicon dioxide that prevented the gelling and gave us good disintegration and dissolution. With the bearding, we implemented a compaction simulator. With small amounts of API, we're able to understand the enteric-coating process to drop the outlet temperature and to prevent the bearding. And what's shown here is the FASIF dissolution. So we saw no dissolution in SGF and immediate release here with the coating increase, so showing a slight slowdown in the dissolution. So the second compound, BCS4 compound, it's a fast crystallizer, and the API came to us and it was degrading in the spray-dry dispersion solvent. So this client needed to go with a spray-dry dispersion for phase 1, and their current development was showing significant degradation and crystallization of the amorphous API. So a little bit of background of the compound. The spray-dry dispersion solvent system they were using was THF water, and the issues, as we mentioned, they saw the bioavailability go from 80% in a solution to about 3% from the crystalline in a suspension. So this is what led to the spray-dry dispersion. And the API was a fast crystallizer. As soon as we put it in water, we saw the crystallization, and that led to inconsistent PKs. A lot of our clients will come to us not characterizing their methicel suspensions using spray-dry dispersions, and so a lot of times they're dosing partially crystalline or fully crystalline material when they think it's actually amorphous. The API is very unstable in the spray-dry intermediate, and the purity dropped during the spray drying process and after about a month of storage. Now, there was previous forced degradation done on the API and supposedly API stability studies, and the dose range for this material was very low. So we had to use techniques like solid-state NMR to detect crystallization of the API at the 0.01 mg per mil drug loading. So the way that we addressed this was first understand your molecule. So really understand the degradation mechanism for the API. And so when we did the proper forced deg, we identified that there was a hydrolysis degradant. Obviously, you didn't want to do the spray-dry dispersion solvent with water, so we immediately took that out. Also, since we identified the hydrolysis product, we added desiccant to the spray-dry intermediate, store at low temperature, and then we used regression analysis to support the reevaluation date. For the crystallization, what we realized was by adjusting the pH, the polymer was not dissolving, and so we were able to then get the physical stability in the methicel suspension for up to 72 hours. And what I've shown here, is the X-ray, and this is with the pH 3.5 buffer, so you see the classic amorphous halos. This is the crystallization without the buffer, but that's interesting crystallization, and I wouldn't necessarily call that a mixture of crystalline and amorphous, but there's definitely a drop in the dissolution and a drop in the exposures. So by implementing the pH 3.5 in the dosing suspension, we were able to significantly increase the API concentration and the PK exposures. So again, quickly understanding the molecule, identifying the issues, we were able to block those and quickly develop a formulation that was going to work. So the third compound is a severely hydrophobic API, and it was going to be dosed as a suspension, as compounded in the clinic for phase 1. So this is, again, a very low solubility compound, and the question probably, well, why didn't they go with the dispersion? The client was moving so fast that they were doing everything in parallel. So we were doing the dispersion development in parallel, but they had their first phase 1 clinical study set to be compounded in the clinic. A lot of our clients will do this compounding using simple suspensions that are prepared actually at the hospital and dosed. And it's not as easy as you would think as just dumping in, and you're well aware, but the client is often not well aware that it can be a very difficult process, especially if you have wettability issues. So for this compound, very low, well, not that, I mean, we've seen lower, but low water solubility, no pH-dependent solubility, no pKa amenable for salt formation. We were simultaneously doing spray-dry dispersion development. What we noticed immediately, though, is the contact angle measurement. So we're dealing with a very hydrophobic compound. Dose range was massive, anywhere from 3 to 500 milligrams, and basically they did not know what their dosing was going to be in phase 1, so we had to prepare for a very large range of dosing. So the API particles in the suspension that would be compounded had to be well dispersed, chemically and physically stable for at least a week, and ideally 2 weeks. Now, also, you have to take into consideration what they have at the clinic or at the hospital. And so for this particular case, they obviously didn't have a particle size analyzer, so you'll see a lot of PLM images because they did at least have a microscope that they'd be able to potentially test if they had any issues with dosing. The API had very bitter flavor associated with it, so we had the taste mask. Wound up that the API was pink, and so we had placebo used, so we had to do some color masking because the API was pink, and this was a double-blind study at the clinic, so neither the nurses or the patients would tell whether they had placebo or API. The GLP formulation before the phase 1 study was just an API suspension in Methocel and Tween, and their PK data was all over the map, right? And so they knew something was going on getting it. Well, that's the problem. They didn't know if it was the formulation or if it was actually what was going on in vivo that was causing the variability. And so what we wanted to do is understand the molecule properties and take formulation out of the equation. So any PK variability they're going to see in phase 1 is really due to in vivo effects. So the first thing we had to do was to choose taste masking, and we chose OroBlend, not necessarily because it was better than anything else, but what we saw is that their technical staff was very transparent. So when we wanted to do excipient compatibilities, we kind of needed to know what was in there. And they were very amenable to sharing information with us and providing that type of information. And the process we designed is laid out here, and each of these steps took a significant amount of research and understanding, but the entire process took us about 2 weeks to develop this formulation for the compounding in the suspension. First thing we had to do was make a paste using the OroBlend, and then we added the remaining OroBlend in the beaker, form a suspension, and the key is we had to sonicate before you remove the spatula. And you might not think that this is a big deal, but there was API that was sticking to the spatula, and so to get the right amount of dosing, we had to do the sonication while the spatula was in there. Then we went through sonication and homogenization. And this took a lot of development, because what you can see here is if you had not enough sonication or homogenation, you actually got bubbles, and the API would just run to the bubbles. And this would lead to non-homogeneous suspension. So the amount of sonication and homogenizing was very well developed. Then we had to put them in amber bottles. Why amber? Because it had a pink color, and we had to mask that pink color. And then the bottle had to be rinsed, and we were able to get a stability, so they only had to prepare every 7 days. So the fourth compound, this is a generic example where we were looking to match dissolution profiles of an extended release freebase. So the innovated drug was a freebase with a polymer-based drug product, and we wanted to replace that with a succinate co-crystal using a lipid-based. So the polymer being softer and allowing for the release of API, where the lipid-based is more hard, different mechanism for release. So we had competing mechanisms going on with the lipid versus the polymer. Just some background information on the compound. And as we mentioned, we're going for a co-crystal, succinate co-crystal instead of the freebase. We had to match everything in the tablets, including size and dissolution profile and dissolution rates. And we were able to get a nice match, good F1 and F2 passing for the succinate versus the freebase. But what I wanted to point out, as you well know, but even though we saw clear correlation in the dissolution, sameness of the dissolution, we saw differences in the fed versus the fasted in vivo. So those are just some of the examples that we looked at over the past few years at Crystal Pharmatech. And our three-step approach, and I just want to kind of get into this just for another minute. Step one, very small amounts of material, late lead optimization, or at candidate selection, benchmark the material, understand how you're going to develop the compound. Do you need a salt? Do you need a freebase? Or do you need an enabled formulation? Go right into the form selection, the one and done form selection. Take that information right into pre-formulation. The data you take here can be transferred right here. Go straight through to first in humans, looking for the tailored formulation, minimal amounts of API, and a high success rate. So thank you very much for your time, and I'll take any questions.
Thank you for a nice talk and a lot of interesting examples. This might be jumping into too much of the details, but on, I think it was the first case study, you had actually decent solubility and then a pretty low dose, or at least a pretty low dose concentration. So I know that you were focused on the tox formulations, but did that molecule, when looking at first in human, still need the enabled technology, or were you able to avoid it?
We're working on that right now.
So next year.
So yes, so it doesn't necessarily need the enabled technology.